Hi everyone, welcome back. In this video we're going to be talking about the method of variation of parameters, which is a method for finding a particular solution to a non-homogeneous linear system. But before we can actually develop the method of variation of parameters, we have to go back and talk about solution matrices and fundamental matrices. So this is going to be a tool that we'll use and that will actually form the major portion of the formula that we wind up with when we're doing the method of variation of parameters. So the starting point here is a homogeneous system, so y prime equals p of t y, where y is an n vector and p of t is an n by n matrix. So a solution matrix is just one that's made up of columns that are all solutions to this differential equation. If we happen to find n of them, then we will have n columns that have n rows, and that will make an n by n matrix, which is the ideal situation. Any collection of solutions can be put into the matrix like that, and that'll give us what's called a solution matrix. But there's a special kind of solution matrix that we're going to be wanting to find, which is called a fundamental matrix. A solution matrix is a fundamental matrix if the columns are independent of each other. How do we know whether the columns are independent of each other? Well, the normal way to find out if columns are independent in a matrix is to take the determinant and see if it's equal to 0 or not. And what we want is not. So that's going to give us a bit of a rule that says that if that a matrix is fundamental, so C of t is fundamental if and only if the determinant of C of t is not equal to 0. And Abel's theorem, which we've talked about in the past, tells us that we only have to check this equation at any time t, because if this determinant is non-zero at a particular time t, then it will also be non-zero at all of the other times t for which the solutions are defined. So that's going to be our check. And that, of course, the determinant of the solution matrix is exactly the same as the Wronskian. All right, so now that we have this idea, or we've been reminded of the idea of a fundamental matrix, we need to prove a few things about them, or at least know the truth of a few things about them. So here's a condensed version of Theorem 4.9, which deals with these fundamental matrices and solution matrices. So this first one is going to come up in the proof we're about to run through. So if we have a solution matrix of this differential equation, then C of t satisfies a differential equation of its own, which is C of t prime equals P of t times C of t. So basically the matrix as a whole satisfies the same differential equation that each of its columns do. Now the thing to notice about this is actually a matrix differential equation. So rather than just having the rows, it has all the different components. We're not going to be actually computing any of those matrices, but we need to know this fact in order to come up with a variation of parameters formula, which we're going to do in a second. Since that's a differential equation, a matrix differential equation, we can also have an initial value problem associated with that. And so if we pick an initial condition, C of 0 as a constant matrix, then there's a unique solution to this initial value problem, which looks just like the normal initial value problem that we have for linear systems, except now with matrices here for C instead of vectors Y. So there's a unique solution to this guy. If the starting point here is an invertible matrix, then the unique solution will be a fundamental matrix. If it's not, right, so basically, if the determinant of the solution of this differential equation is non-zero at the start, then it will stay non-zero forever. And then finally, we have a bit of a connection between different fundamental matrices. Because remember, you can make a solution matrix or a fundamental matrix by just taking any solutions and making them the columns of a matrix. Now, you can do that in a lot of different ways, and many of them will be fundamental matrices, many of them will not. And we'd like to know if there's some kind of relationship between the different fundamental matrices. Like, so if I take a fundamental matrix and then I change it around somehow, is the result still a fundamental matrix or not? And this is that relationship. So if C of t is a fundamental matrix and Psi hat, so notice the hat there, is a solution matrix, then Psi of t equals Psi of t hat equals Psi of t times some constant matrix C. So basically, if you start with a fundamental matrix, you can get every possible solution matrix just by multiplying by another constant matrix. And if that thing you multiply by is invertible, then the new thing you get will also be a fundamental matrix. And that goes both ways. So that's an if and only if statement. Now, that's pretty heavy on the theory right there. We're going to make use of that in a very practical setting, basically right about now. We're going to go over now to the non-homogeneous system. So we have the same equation base as before. So y prime, vector y prime of t equals p of t times y of t plus, and now we have this non-homogeneity that we're adding on. And we have an initial condition. So this is an initial linear system of differential equations and an initial value problem. Now, suppose that we have a fundamental matrix for the homogeneous system. So this is basically going to play the role of the complementary solution, right? Because every column of this matrix is a solution, and we have enough of them, and they're independent. So that's all of the information you would normally have in a complementary solution. And in fact, the complementary solution is exactly the fundamental matrix times some constant vector C. Right, so basically C1 times the first column plus C2 times the second column plus C3 times the third column, and you get your complementary solution. Now remember that in the method of variation of parameters, when we did this with single linear equations, non-homogeneous equations, we started with our fundamental solution, our complementary solution, and then said, okay, well, what if we multiply each component of the complementary solution by some function u, u1, u2, and then figure out what has to be true about u1 and u2, and then by putting that together, we can figure out a particular solution. And that's basically exactly what we're going to do again, except now in this very compact form, because now we're going to say our particular solution is going to be the fundamental matrix that we have times some function, vector function u of t. Now, so we're just going to assume that that's a particular solution and go for it and just kind of see what we come up with. We're going to assume that's true, plug it into the differential equation, and see what comes out. And so now comes the let's do a bunch of equations phase of this thing. So we're going to assume that, again, yp has this form here, and we're going to plug it into the differential equation, which we see right up at the top there. Right, there's our differential equation. So let's go ahead and do that. So on the left-hand side here, we're going to have c of t, u of t prime equals p of t times y of t, let's see, and that will be, so that's p of t times c of t, u of t, and then plus g of t. That's a vector there, there, and there. Since I don't write in boldface. Right, so over here on the left-hand side, we're going to have to do the product rule to get the derivative, and let's see where that leads us. So we get derivative of the first plus, now we leave the first the same, and multiply by the derivative of the second, and the right-hand side of this equation is going to stay exactly the same. All right, so now is the first time when we're going to use one of the facts that we had in the theorem that we just covered. So basically what I'd like you to look at is the first term here, multiplied by u of t, and the first term on the other side of the equation, also multiplied by u of t. So what you'll notice is that we have here c prime, and on this side we have p of t, c of t. And our theorem said that those are equal to each other, right? That C prime equals P of t times C, that it satisfies that differential equation. So that means that these two terms are equal, which means that they will cancel. And that leaves us with a simplified equation, right? So now we have that C of t u prime of t is equal to just g of t. So that's great. That's much simpler than what we started with. And now what we'd like to do is still solve for u prime of t, which means we need to get it alone. And since it's a derivative, then we're going to need to anti-differentiate. So we need to get this c of t off of the front of the equation. How are we going to do that? Well, we just have to left multiply by its inverse. So that'll cancel out, multiply, become the identity, which disappears on the left-hand side, and on the right-hand side, it'll still be there. So we get u prime of t is equal to c of t inverse times g of t. Right? Now, what I'd like to do is integrate both sides of this equation. We're going to be a little bit more careful about integration than maybe we usually are. We're going to do this as a definite integral on both sides. We're going to integrate the left and right-hand sides from t0, which we'll recall is the time at which this differential equation starts, right? So if we're going to go from t0 to t, whatever it happens to be. That's going to help us come up with a nice, useful formula in a second. So I need a dummy variable on the inside of my integration. So it's going to be the integral from t0 to t of u prime of s ds, that's the dummy variable, equals the integral from t0 to t of c, I'm going to move that inverse in here, s g of s ds. All right, so hopefully that's clear what's going on there. Now on the left-hand side, we have the integral of the derivative of something. So that will just be u of t minus u of t0. And on the other side, well, we can't do anything with this. We have no idea what the equations are, the integrand here is. So we're just going to have to leave that as a formula. t0 to t, c inverse of s, g of s, ds. All right, so that's where we've gotten to. And we can bring this over to the other side, right? We're just going to call that u0, and that will give us a formula for u of t. And so let's take a look at what we've got now. Okay, so we didn't need that space. So we've got ourselves the equation here. U of t is equal to u of 0 plus the integral from t0 to t of c inverse of s, g of s, ds. Now, this thing here, this is a constant vector, and we can choose it to be anything we want. Right, because we're just looking for any solution, anything, any u of t that we could pick to make a particular solution work out. So why not let u 0 just be the 0 vector. That'll simplify things. So now just think that that's not there. When that's not there, we're in business. So now we know u of t. Remember, we were looking for a particular solution of the form, right, yp is equal to c of t u of t. So to get our particular solution, all we have to do is multiply this thing that we've just gotten, right, this guy here, multiply that by c of t. So you have c of t integral of this thing. Now it's important here to notice that the two c's here, here's c and here's c inverse, they do not cancel with each other. This one is inside of an integral, cannot be brought out. It has an s in it, right? Dummy variable can't be brought out of the integral. And while we could bring the c of t in, it would be c of t, c inverse of s those don't match up. They're not actually inverses of each other because they're being evaluated at different times. So this formula gives us the solution, right, or the particular solution that we need. Then to make a general solution, we just need to take our particular solution, which there it is, right, our particular solution from above, and add the complementary solution, which is right there. So those are the parts of our formula here. We have the complementary solution, and we have the particular solution, just like we always do. And that's the variation of parameters formula. Well, it's not quite the variation of parameters formula because we still don't know what is this constant C. Remember, we started with an initial value problem. So when you have an initial value problem, you should be able to figure out all of the unknown constants, and that's represented by the vector C. So can we figure out the value for C? And of course, the answer is yes. I wouldn't be asking the question if the answer wasn't yes. How can we do that? Well, we're just going to plug in our initial condition. So to find C, plug in the initial condition. And the initial condition was y of t0 equals y0. So we're going to plug in t0, both sides of the equation. Y of t0 is equal to y0. So what does that give us? That gives us y0 on the left-hand side equals c of t0, c, plus c of t0 integral from t0 to t0 of some stuff. We don't even care what that stuff is because we are integrating from t0 to t0. That's all equal to 0. Right, so this whole part here just becomes 0, and we're left with a much simpler version of this equation. We have y0 equals c of t0, c. And now to find c on its own, we left multiply by the inverse of our friend here, c of t0, and that gives us that c is equal to c inverse of t0 times y0. All right, and last but not least, in order to have the variation of parameters formula, all we do is we take this formula for c, right, and we are going to take that and plug it in right there for c. And that will give us our final version of the formula, the variation of parameters formula. All right, and take a look at what that is, if I can get this to slide properly. There we go. We get the variation of parameters formula in all its glory. It is not the prettiest thing we've ever seen, but it is really, really useful. So there it is. There's our particular or our complementary solution, c of t times something. This we've just figured out is c. That takes care of the initial conditions. Make sure the initial conditions are satisfied. And then over here on the right-hand side, the far right-hand side, we have a particular solution. Basically, this is the unique solution to the initial value problem. So this isn't just a method for finding the particular solution. It solves everything all at once. It finds you have to have had the complementary solution to start with, the fundamental matrix. Once you have that, this gives you the fundamental solution, or the fundamental matrix leads you to the complete general solution and also takes care of the initial conditions, so you have the unique solution all in one fell swoop. That's a little bit why it has to be quite as ugly as it is, but you can do it. You can go, and this formula is also useful for proving theorems because you know that you have a nice formulaic version of the solution that you can just use and prove properties about. So that's the variation of parameters formula. What would a problem like this look like? How would you use it? Well, this is an example of a variation of parameters problem. We have a system of linear equations. It's non-homogeneous because of the e to the t, and it has an initial condition. So we should be able to just plug this all in to the variation of parameters formula and pop out the unique solution to this system. And indeed, we can do that. That's covered in the next video, which is a worked worked problem video with this exact problem. So go ahead and watch that next one if you want to see how this works in practice.